Yeah, cool.
Okay. So before you get started,
Yeah, is it visible?
it'll take a minute. Uh, okay. Yeah, it'll take a minute. So meanwhile, yeah, we can see it now. So meanwhile, let's get some quick reviews. So since Biswajit, you're already unmuted, can you tell everyone a bit about what your group worked on this week? How's the progress been?
Okay, so far we have done with the theory work and the first 3 weeks. So we are only left with the 1 week. So right now we are doing a course in Coursera called the Data Driven Astronomy. So in this PPT, I will tell you yeah. Let me just don't give a spoiler. When I will be sharing this, yeah, I have all the summary actually. When I will be presenting this, so I
Hmm.
will start like what I have done in this week. So
Okay.
I and
Yeah.
Maria just start.
Okay. So Shashank, are you there from White Dwarfs?
Yeah, I'm here.
Yeah. So you can quickly tell us in 2 or 3 sentences what your team worked on this particular week.
My team has worked on learning LaTeX so that we can prepare a proper report. I have assigned to my team a section of the report that they can work on. I
Okay.
believe we are done with the introduction, the most of the theory parts, the problem statement, everything. The only thing that is left for us is the methodology, and we just have to implement the algorithm. I believe we are very close to finding the limit on our own.
Great, great. So, meanwhile, the problem solving itself, the mathematical part is done. Everyone is on the.
Yeah,
Okay, great. Right. So, some of the coding is still left.
I'm doing that right now actually as I speak.
Okay, no problem. That's good progress. Great. And yeah, I think rest of the teams, please, like catch up because I would like to remind you all that this Monday onwards, it's the last week. So tomorrow you have, I think, 2 sessions consecutively. One is both of them are very interesting. One on detection of gravitational waves, the other on rocket engineering and basics of orbital mechanics. So I will be announcing that, but basically, I want to let you know that there are 2 sessions tomorrow. So there won't be any time for journal club and stuff. So Monday onwards, you have exactly the next 7 8 days to wrap it up with your team. So if you have not started on a report, if you have not started on, at least we expect a very good maybe 50 slide presentation. You can ask your whole group to contribute to that. But the ideal case, of course, is you have a full report done. So yeah, get started on that. Can we have Vishesh?
Yes, since our group is more on like theory, so you know programming work to do there.
Yeah.
And like Vikrant had informed us last week, the end of last week about this report. So we've actually started it last week, like end of last week.
Hmm.
But then the pace was very, very slow. So then we divide the team into like various categories and who has to do what.
Okay.
And after doing that, the work picked on like some pace, and we've submitted the draft to Vikrant, and
Great.
he's put out some suggestions also, and that is nearly complete. So by today evening, like today night, we'll submit the final report, like
Okay.
of all what we learned and all that.
Wonderful. And
The
finally, yeah, is there anything else you want to add?
the like we had planned a debate, like inter team T1A versus T1B debate,
Correct.
but because of this report, like that got postponed now because most of them are working there, and like it's pretty tough to focus on both the things at once.
Yes,
So
yes. It's always better to minimalize and work on one thing a particular week.
so next week, the beginning, like first 3 days, you might have debate on any of those days.
Okay. I think you also had a quiz, right?
Yes.
Okay. I'll speak to you personally. Maybe if we can host that quiz again for everyone else in Equinox, it'll be nice. Just give me the questions and stuff. Okay. And finally, Sanat Kumar, are you here? I think he's not here. Is there anybody else from T1B?
Yeah, I'm there.
Hi, sir.
Yeah.
How has the week been? And
You
did you
see,
all?
Yeah, Sanat Kumar is the group leader for the entire group, and Namita is the team leader for Lambda CDM. Sanat Kumar
Okay.
is in the Mont.
Okay.
So I don't know actually how they are going, but on my own, see, because since I am in a Lambda CDM group,
Uh-huh.
so I'm taking care of the first understanding Lambda. It has three components, basically the derivation, then redshift, and the Hubble constant. So these three issues have been deeply involved in the last 2 weeks. So this is my from my side. Regarding on the group side, probably they are the best people to tell about it.
Okay, no problem. So, Chakradasa, would it be okay if we came back to you and you talked a little bit more about Lambda today? Can you spend?
Uh, Actually, in a articulation, I am not. I don't know how to articulate. Maybe next week.
Okay, fine. Yeah, you don't have to make like any fancy PPT, but if you have some method to explain it, you can try. So we would like it if you presented once in the journal club.
Yeah, maybe next week I'll see. Okay.
Okay, sure. Yeah. Yeah, we can do that. So yeah, do remember that next week we are going to be reducing the number of lectures slowly from now, because we want you guys to put more work into the project in the final week. So we won't bother you too much. Maybe just SQL sessions, and maybe you guys can request specific technical sessions. So that's all we'll have, and we'll slowly reduce the pace so that everyone can settle down and work a bit more. So yeah, next weekend is a good time to present. If you've not interacted much in the groups, this is your chance. So next Saturday, Sunday, you can present to the whole Equinox. Uh, yeah. Okay. So Biswajit, you can get started now.
Okay, Mariam, are you there?
Yeah, I'm here.
So let's begin.
Okay, so hi guys. I'm Mariam Hashim, and Biswajit and I are going to be giving a weekly summary of what the Pulsars team has done this week. So that which is mainly programming image stacking. Next slide, please. So this is a brief of the content that we have today. So first we're going to be talking about pulsars. I mean, surprise guys, the pulsars kids are talking about pulsars. What were you expecting? But from there, we're going to move on to thinking about the data you get from pulsars, right? And it's not just about data from pulsars, but the data you have in your computers and what you can store, and the challenges they present, and then what we can do with that data, and hence image stacking. And in the end, we're going to have a brief programming session. We're going to be showing you a few programs that we learned here. They're very basic Python programs that we learned on a course that we joined on Coursera, which was data-driven astronomy. So moving to pulsars. We've already dealt with this. Pulsars are highly condensed neutron stars spinning at exceptionally high velocities, mainly due to conservation of momentum. They keep spinning, and this speed is what causes their magnetic and electric fields to increase. Now, these fields are also responsible for the beams that shoot out through opposite ends, through the poles of the magnetic field. If you want more information on that, I would recommend reading papers on the light cylinder theory, which is so far the most accepted theory on why pulsars emit radiations in the way they do. So moving on to data. I did mention that pulsars only emit radiations in the opposite poles, right? So unless you're on the plane of emission, you actually won't see anything. So that already is a disadvantage. Even beyond that, the pulsar spins at exceptionally high speeds. So it's basically like a lighthouse on steroids, if you will. And that data has to come from a very far distance to us. And hence it is very, very, very faint. It's very faint. And considering the noise that we have in our environment right now, it's really hard to basically read that data without being confused by all of the noise there is. So Biswajit, the next slide, please.
Yeah, so far, like as Mariam explained about the data is the most important thing, the parameter that we are going to deal. Like in previous day, we used to do everything like the instruments were available, but right now it is completely digital. And due to this advancement in the technology, we are getting a huge number of data in petabytes and exabytes. So just for a brief, I can show you. This is a kind an image. Let me just shrink it down. Okay. So as you can see, this is a image I have taken from a report. So this is the first image. So you can see the signal. Actually, this is the actual signal, but whenever we try to receive the signal, it's actually in this form. Okay. So what we are trying to is to trace the path of the signal, and this is the final form of the signal. So the signal is always introduced with noise. So what we um, in this week what we are trying to do is did some programming and try to reduce this noise, like how we can we try to find out any optimized solution to reduce these noises. So this is I won't go in brief about this because we have very less time, and this is another very beautiful signal. As you can see, like you can see the period. All right, it's so beautiful, like and these are very as Mariam already said about the signal is really so faint, so getting this signal is really a great achievement. Okay, so yeah, moving to next, challenges of modern world. Challenges in a modern world. So yeah, there are various challenges in the modern world. So there is the AME factor. Then comes the strength of the pulsar signal. Then there is the nature of the signal, effect of scintillation, effects of dispersion, droplets effect, and polarization effect. This all this application has a, when we try to go in deep, there are so many things to learn, but due to the time thing, let me just give a small explanation to this. The EME factor is nothing. It's called the Earth to Moon Earth factor. Earth Moon Earth factor. So the meaning of this problem is that it's when we are trying to deal with pulsars, it's not which is like as close to Earth like the Moon. So the factor when we are trying to calculate any signal, so that we have to always consider that yeah, pulsar is something beyond our solar system. It is somewhere far from our galaxy, or it is in our galaxy. So first problem is that we cannot consider this factor. The second is the strength of the pulsar signal. As Mariam already told, the signal is very faint, and the unit of the signal is Jansky, where 1 Jansky is equal to 10 to the power minus 26 watt per meter square, I guess. So the signal is so faint. If you want to if you want to light a bulb, it will almost take thousands of years to light a bulb with that signal, because whatever signal we are receiving is in the radio form, and radio form, when we are trying to detect in our instrument, it is coming in the form of power. So that power is again transferred into the FITS file and all those images. Then what we are seeing in image, actually the pulsars, the signal what we receive. So I won't go in much details about this. Then next go to the nature of the signal, and then the effect of scintillation. For a small demonstration, I can say in previous day you used to use kind of an analog type of cameras, where there were used to be a reel. So just for a kind of like you can also try, if you find any camera, just a real one camera. So what you can do is just try to open that, and you will see if it comes under the exposure of any bright light from outside, you will see that your image gets spoiled inside. So this is very important factor. It is having an advantage and as well as disadvantage in this radio signals. So this is also a great challenge. Then comes the dispersion, of course, due to the interstellar medium in our space. and then the Doppler effects and polarization effect. So with this, I will move to the next slide. Okay, let me reduce this. Okay, so this is the most beautiful image. So like we have also seen in the other lectures also, like most of our mentors has and guest has give this image in their picture. So as you can see, this is our Earth's atmosphere, and these are the electromagnetic spectrum wave. So starting with the shorter wave called the gamma to the longer is the radio waves, and only the radio waves is the uh, only waves that can penetrate our Earth atmosphere, and even others also can penetrate, like visible also penetrate, but that observators should have to be in certain height, like it has to be atop of the, beyond these clouds and all, so it has to be in very top of any mountain. So that is really a very expensive way, like to take all the instrument and the management thing, like taking care of this instrument. So it is kind of expensive, but radio is very advantage for us, like we can, due to the longer wavelength, we can directly receive the fainter to fainter signal, even the low frequency signal also we can receive using the radio. So this is the great advantage. That is why, like, we are using this. Okay, so let's move to the next. So far we just came across the theory. Let's move to the topic directly. Let's dive into the image stacking. So let me divide this image stacking into two. Like I will first discuss with image, what is image, and then Mariam will go with the stacking part. So what is image? Like when image, like whenever we think about image, what does come into your mind or everyone's mind? Like it is something, a kind of a representation of some kind of a form. Okay, so with this, the smallest element of an image is called the pixel. So right now I'm going from theory to the little electronics. Okay, electronics, digital electronics. So as you can see from here, the pixel is the smallest element of an image. So each pixel correspond to one value. Okay, in this given picture, I will just demonstrate you. Okay, so actually, pixels are of three types. One is grayscale, one is black and white, another is RGB. So I am just trying to discuss about grayscale. Those are some different topics I'll discuss in further other meetings. But right now, let me discuss about grayscale. So because I am having an example, live example. So as you can see, one in a 8-bit grayscale image. So this is an 8-bit grayscale image. So the value of the pixel is can you okay, let me tell you like why it is 8-bit, because the grayscale image lies between 0 to 255. So 8-bit, if you change into this, like how you've done is 2 to the power 8. 2 to the power 8 is 256 pixels. So from this we can get the value of the pixel between 0 to 255. So suppose this is an image. Just suppose this is an image, and you can see this square box are 1 pixel, and every pixel is having some value. So these are nothing but the value of the pixel. So the more the dark is, it is a 0. The more it is light color, it's the it is 255. Okay, so if you try to plot in this way, this is actually a matrix form of this image. You can see these are the values. Okay, because computer can't process, like a computer doesn't understand what is image, what is pixel. It only understand the logical values. So this is why how it is done. Okay, so next moving to what is stacking. Mariam, just carry forward.
Yeah, so stacking is, in simpler terms, layering of images so that we get the average of them, right? So again, I mentioned way in the beginning that the signals we receive are very, very faint. With these signals, they're often covered or shrouded over by the amount of noise we have here on Earth. One of the issues of living in a modern world, your phone produces more electromagnetic radiation. No, no, no. Your phone causes more interference than you can expect a pulsar to give you signals. So the solution that scientists have come up with, is to take one set of data and to layer it with several other sets of data taken over a longer period of time, so that the noise is cancelled out, right? So +1 and -1 are a 0. So they're completely cancelled out. So what you're left with is a clean, crisp image. So you can see in this little set of photos we provided here, the first frame isn't as, with just one frame, it isn't as, I mean, it's clear and it's pretty, but it isn't what it could be. So as you keep increasing the number of images that you've stacked, you get more clarity as the noise is cancelled out. Now moving on to image stacking with statistics. Sorry guys, it has statistics. Statistics is a branch of mathematics dealing with the collection, analysis, interpretation, and presentation of masses of numerical data. It's basically a collection of quantitative data. So we basically tell the computer through our programs how we're going to layer these images and what we're going to do with them. So beyond this, we're going to be moving on to the programming bit of our presentation. So in statistics, all of you might have done in your basic 10th grade that it begins with mean. Mean is basically the average of a set of information given. So if I give you a whole set of values, you're going to add all of them and then just divide them by the number of values you had to begin with. So you get what you assume is smack dab in the middle. And that's basically what we do with the program.
Okay. So yeah, so thank you, Mariam, again. So let's move. Okay, so right now, can you hear me?
Yeah, we can hear you.
Okay. All right. So yeah, we have done so much again the theory part. So let's move to the coding section. So I will try to demonstrate few codings, and I will just try to explain you like we have done the theory part. Now let's move to mean. So after doing this programming, then we will try to slowly tell you like why we are doing this. Okay, so let's move to the mean. So this is the program. As you can see, basically what I am trying to do in this program is, as we know that mean is the, suppose we have a data of this, these are the elements, 1 2 3 4 5 elements are there, and if we want to try to find out the mean of this element, so what we can do is the add this all and divided by the number of element. So by that we can find out the element. So let me just play let me just run it. So here we are. So as you can see, we got the value 23.96, which is the mean. This is calculating manually like we do in our uh, copy or pen and paper. So now let's do it within using a Python library. So we have a module called statistic in our Python library, which makes it more easier. So we don't have to write all these formulas, and we can just directly hop in and we can just import this file. We can, from statistic, we can just import direct the mean, and just we have the array. As you can see here, we have the array, and then we can just write a m of mean, m fluxes, where fluxes is the data, and just we can play it. You can see we got the same data. So this decreases our using of, like when we go to a larger size of programs, lines of course of program. So using the this library, it decreases the time consuming. Okay, so moving to median, Mariam.
Median is very similar to the mean, but again, you aim for that middle number in the same way as you do with the mean. But the difference here is that the median is actually the middle number. So you basically sort the data that's given to you in ascending order, and then you pick the number in the middle. That's basically the median. Now, mathematically, there are two ways of doing this. If it's an odd number, you have something in the middle. Now, if there's an even number, obviously, there's an issue. You have two numbers in the middle. So you have the formula where it's half of the middle number minus 1 plus the middle number, what you would get when you divide the even number by 2. So that's a formula that you've done this basically. And then in the manual calculation, we do the same thing. Biswajit?
Yep. So thank you again. So here we will just try to demonstrate with a program. As you can see, like I will just try to add to Mariam, like whenever we try to do a median of any number, the first step is to sort that number. We sort that number either in increasing or decreasing, and then what we try to find is the mid of the number. So as you can see, if anyone is not aware of the coding, so just I will give a small um, information about that. So we are trying to this is length is the function which is taking the elements, like how many elements are there. So suppose here is 6, and when this is the sign, like this is in this list format, so we are trying to convert it into the integer format by double slash. So if we use the divide by this slash, then we will get only the integer one, the float one. Suppose there is 7 number of number is there, then 7 by 2 is 3.5. So we don't want that 0.5, because that 0.5 3.5 data is not available in our data set. So by this again we have the median, and we know that how to find the median, and by this we can find the median. So in this case we got the median somehow 20.7. So you can see, like just imagine here like this, that put the data in increasing order, starting with 16.2, then to 17.3, 20.7, 22.3, and 70.1. So by this we can find out that, yeah, 20.7 is the mid value. Okay, so 5 terms, mid value is 20.7. So this was the odd part. Now let's think about even part, how we'll deal it. Because whenever we are trying to do with even thing, so how many number is there? 1 2 3 4 5 6. 6 elements are there, and if you divide it by 2, if you try to find out the mid position, mid value, we can't find, like what should we take? We should take this one, third place, or the fourth place. So there is a formula, like what we can do is the fluxus, which is this data. First is the method, as I said, we have to sort it down, and then mid minus 1. Mid minus 1 is something, if it is a 3, if the mid is 3, then 3 minus 1 is the second position. So plus fluxus mid, and if you divide by 2, we will get the median. Yeah, so here we go. As this was the event, so that is why you can see this is 20.0, which is almost near to this 1 2 3 4 5 numbers. Okay, so there comes the advantage of the median, because when we are trying to calculate mean, suppose just imagine take an example, suppose 1 2 3 4 5 and 100. So if you try to find out mean of this, we'll get somehow so we will get some number which is between like this and this set of numbers. So there will be a huge gap between this thing. So what does median do? Median try to bring that element which is almost near to every element in this data. So that is why we have went to the median algorithm, because by mean we can't find the exact. When the data is very more, then the technique is very robust. So yeah. Okay, so Mariam, NumPy.
Now NumPy, right? So Biswajit mentioned this. If you're going to use the method that we used before, it's going to be a very lengthy thing. There's more data that's going to be used, and it's more time consuming. To avoid this, we actually use a library that's available in Python called NumPy. So NumPy is a library that works with arrays. And so indirectly, you get to work with matrices too, since they're also represented as arrays. Biswajit mentioned that the median is a more robust technique of finding the average data, if you will. So if you look in the graph that we've provided there, you can see that the red line is the mean and the blue line is the median. And the median is actually much more closer to what the average value would be than the mean is. So to demonstrate this, we've run a program using NumPy with a set of values that would generate different means and medians. So Biswajit?
Yeah, so we have came across mean and median. So let's give an example, small example, so it will be more understandable to everyone, like what we are trying to say. So let's run this program. Okay, so you can see here the list of data is same, but the values are different. All right. So as you can see, this is the way you can import the library, and this is the function. So I have used the NumPy library, direct np.median. I don't have to write so much of formulas and all. I just simply can easily write this thing, and by this I can reduce my number of lines of code. So I'm just passing this all the data over here, and it is returning the value of the median and the mean. So the median is, you can see, checkout, it's 2.55 and the mean is 5.175. And now take this element. So when you're dealing with this all elements, you can see like whenever we're 2.5 is somewhere nearer to this and this and this. Okay, and when we are taking a 5.175, you can see if you try to make the difference of every element, you'll find it is increasing. So that is why we are using the median technique. Okay, so moving to fits images, Mariam, fits file.
Right. So again, data you've already, so during observation, you've already got your set of data. Now, how is it stored? For this, we're using FITS files. FITS stands for Flexible Image Transport System. So it's basically a numerical array, right? So it's a two-dimensional array with one representing the header of the data that follows in the arrays it's connected to. Astronomers use this a lot since it's much more simpler. As it's in the name, it's flexible, and we actually access it using the AstroPy module. Um, so here's the thing about FITS files and how efficiency is very important. In an average sitting, you get about 6 lakh images of data, right? So one image, depending on the dish you're using, if it's a radio telescope, the dish, on average, you get a 200 by 200 layout of an image. So that is 40,000 pixels. One pixel takes an average of 8 bytes of data, right? So the total memory required to access all of these images will amount to 192 GB of data. Unless you have a PC that has like 200 gigabytes to spare, it's really inefficient. Your system might just crash. So to avoid this, we have algorithms that work easier, that work better and more efficiently. And beyond this, we have a video after this, which is basically going to show you what image stacking in itself can do. So here you can see that they are layering images one by one and finding the average. And as they are doing it, there is more clarity, and you end up with this little black speck in between, which is a consistent emission from a pulsar. You can actually see the amount of noise that has been cancelled out and the amount of nonsense that was actually being recorded, right? So this is the advantage of layering images. And what better place to use it than with pulsars? You can't basically see them with these anyway. So Biswajit is going to continue with the algorithms.
Okay, so the thing is, as Mariam said, like basically we are trying to reduce the signal to noise ratio. We are trying to reduce the noise, the SNR of that particular image. So the more the number of images, the more precise we can get the data, the more precise signal we can get. So yeah, as you can see, starting at 20 images, so much of it has been reduced to just a single. So this is our actual source. Okay, so moving to next, I won't take much time actually. So this is some code okay, so should I explain? Okay, so this is a code, like I am trying to demonstrate like what time it takes for suppose, okay, so we are importing time function as we are dealing with the time, because this code, what it will take, like suppose it is in my PC, it is showing 21.70. So it is just running the time function and it is trying to calculate how much time it takes to perform a certain number of data. So we are using here NumPy as NP, and we are taking a data of 10 to the power 7. Just imagine the number. So we are taking the data of 10 to the power 7 using the random function. We are just trying to get a random values of 10 to the power 7 of data. So start is basically the to start the counter. Counter is nothing but just to start something, like we have to give a signal to that counter. So this is a code for that, and this is a function. And then if you try to find out the mean of the data, suppose we have this 10 to the power 7 enormous number of data, we try to find out the mean. So let's calculate what time it takes. Let me enter it. Okay, it is taking time because okay. So you can see the data, it took almost around 4.9 seconds to process. Now in the next this I will introduce like how we can optimize this signal. Just I haven't done much, I haven't introduced much. You can see I just changed this code. You can see here, this is the handwritten one like we do in our normal node copy. This is the coding version of the optimized version. Now let's see how much time it takes. Sorry. Let's check out, guys. Just look at this number. So this is 0.03 and 4.99. So you can see like just only single line I am reducing the time so much. So timing isn't enough. Okay, so when we are dealing with this kind of images, timing is not at all enough. The next thing we are going to say about the memory, because memory also matters whenever you are trying to uh, uh, take, like as Mariam said, about 192 GB of data, how we can shrink that data. So our next goal in this week is to learn about this memory management. We have so far completed till the time management, how we can optimize the algorithm for time. And I haven't went very brief here because actually time is short, and I'm sorry again to everyone, like I have too much time here. I'm presenting my PPT only, our PPT. So yeah, so this is a basically function. Let's say okay. So as you can see, this is I'm importing a system module, like, and you can see here a equal to 3, and you can see how much byte it is taking. It is taking 28 byte. So this is a 3 value 3 assigned to a. So it is taking 28 byte of the system. Then coming to this float number, it is taking 24 bytes, and coming to this, it's taking 80 bytes. A is 3 and B is 3.123. It is taking 80 bytes. Coming to D, it is an empty set, but still it is taking 64 bytes. So using this program, we can find the how much it is taking. All right. So with this, yeah. So we have complete so far, and right now we are the next goal is to come up with a good memory management, the optimized way, and we are trying to deal with the fits images. And yeah, so this is our goal, like optimizing the space and time of the data and come up with an optimized algorithm.
Okay, great job, both of you. That was very, very informative. So do send us the PPT on Journal Club. Very nicely made presentation as well. So very good. Does anyone have any, questions or comments about Biswajit's and Mariam's presentation?
Actually, another thing is like I want to add here, like you can, this Jupyter notebook is really very great if you want to do presentation and you want to do coding parallelly. You can use this platform, and it's really
Yes, I think some of you are discovering Jupyter Notebooks for the first time. It's one of the most popularly or commonly used tools, both for keeping or documenting your progress, especially when it is code related, but also for teaching yourself how to code also. So it's very effective. So please use it. Okay, let's quickly move to Shashank's team. I think someone, Sagar, was supposed to present today.
Can Pulsar's team member himself comment on this?
Yeah, you can comment.
Biswajit Bhaiya and Mariam Didi, both of you, thank you for summarizing our whole week's progress in just how much? I don't know how much time you took, but yeah, you took quite short time and you did it very well.
Yes, yes.
Well done.
You've inferred everything very well. So yeah, I think with
Thank you for explaining it so well and
yeah. So
yeah.
once we do, the final algorithm and for bigger data sets, I think the final presentation can be a bit more elaborate. Okay, so but yeah, I think that was a very good example for how or what we are expecting for the final presentation, guys. So it should start conceptually like how they did, and you can slowly move into the code and the algorithms and or whatever the basically the essence of your project. Okay, Sagar, which team are you from? Are you still here?
Yeah, I'm from T1E.
Sure,
Can
you're
you?
going to present today, right?
Yes.
Okay, can you screen share? Yeah.
Am I the host now?
No, you can still share the screen. We have given you permission.
Okay, okay.
Yeah, and like I mentioned, this is a great opportunity for anyone to kind of come up and talk about what you learned this week. You don't need to have a presentation or a paper. You can also just talk about your academic learnings. So remember that Journal Club is just for information exchange. So yeah,
Can you see the screen now?
yeah, great. Go ahead.
Okay. So actually, Biswajit was explaining very nicely, but since our week today we had the report to do, I didn't have much time to make a separate PPT. So I'm just explaining what I have done this week. So this week, everybody concentrated on their reports. So I concentrated more about evidence and nature and detection. So, evidence, we have main evidence of galaxy rotation curve, which was used from earlier times. So basically by Newton's law, we get that V is equal to square root of Gm by R. So, but what the scientists saw that is it has to increase and decrease actually because of many other stars which are interfering, but actually what was observed was it's just increasing and it was a constant. So we can see here that dark matter in this picture, you can see we have center of the galaxy and galaxy disk and dark matter which is in blue shade, it is going on increasing. So because of this, we see that orbital velocity of stars to be a constant. So that's very simple mathematical change. So if we substitute this m to m naught r, so as r increases, even if mass increases in such a manner, if we substitute, we get that orbital velocity to be a constant, some gm naught. So that's how we see that some matter is increasing from center to the outer edge of the galaxy. So another evidence is extended emission in X-ray observation of galaxy cluster. So there is a theory that in surrounding galaxy clusters there is a hot gas of whose particle velocity is 1000 meters per second and temperature is 6.6 some Kelvin. So if we apply black body radiation to that, we get that the radiation emitted is mostly in X-ray X-ray radiations. So, and what was the final result was to hold that much amount of gas which is moving at very high speeds, the normal matter of galaxy is not enough. So there has to be some extra matter that is holding the gases together. So that's what extended emission in X-ray observation of galaxy clusters tells us. And the most important tool is gravitational lensing. So gravitational lensing is a proven fact. So if gravitational lensing gives any other extra observation, so that is also a true one. So we see that in normally if normal matter is present, we see gravitational lensing to occur. So here you can see in this picture, due to a presence of some black hole or some heavy mass density object, the behind objects are lensed. So in some parts of the universe, even if there is no normal matter, see in this image you can see the border ones are lensed, and in between there is no a heavy mass object, there is no black hole, neutron star, there is nothing else. So even though the galaxies are being lensed, so this was observation done by scientists, and they came to know that it's because of density of high density of dark matter present. So that's why we see this uh, bending of light, which is happening by itself. So in similar manner, the scientists mapped the dark matter regions in our universe, and they got this image. So this image is the uh, presence of dark matter in our universe. So we see that these dark blue shades are dark matter, but this picture is clear. We see each and every yellow dots are galaxies, and the dark blue things which is surrounding that yellow is dark matter. This is one clear picture of dark matter. And coming to nature of dark matter particles. So dark matter particles, many in previous presentation also we said that they are very slow, electrically neutral, non-baryonic, like that. So coming to mass limitations. So mass limitation means, so dark particle should have one mass. No. So how will limit that mass? So we use uncertainty principle, quantum mechanics, and Newton's law for that. So we get that V is gmm by r by Newton's law. And if we apply quantum mechanics and uncertainty principle, the derivation is very big. So I just put the final formula. So this is the radial distance of dark matter particle from center of galaxy. We get the formula to be this, which is Planck's constant, gravitational constant is g, m is mass of galaxy, and small m is the dark matter particle. So we know that this var value should be such that it should be in the galaxy or in the edge of the galaxy. So applying that constraint, we get the mass of the dark matter to be this 10 power minus 31 GeV by c square to 10 power 50 GeV by c square. So if any dark matter particle exists, it has to be in this range. So we get the mass limitation like this. So if you, and we know that dark matter particles interact with themselves, though they don't interact much with normal matter, they interact with themselves. No. So the scientists calculated even that. So they said that the interaction should be less than 35 kpc by r, that is 35 kpc per r for a typical scattering cross section of 1.75 into 10 power minus 25 centimeter square. So this is the value which scientists got, that is 35 kpc per r. That actually that value is very low. So the interaction between the dark matter particle also should be very small. So now coming to detection of dark matter. So we know that dark matter is one of the biggest mysteries of our universe, and scientists are spending so much time on that to understand dark matter. But scientists said that WIMP particle is very promising candidate for becoming a dark matter particle. So even though they failed many times, that particle is very promising one. So direct detection of dark matter. So there are many methods and techniques for detecting the dark matter directly. So one simple mechanism is energy transfer. So in this transfer mechanism, what we'll do is we'll transfer the energy of dark matter particle to the detector particle. So we know that the interaction is 35 kpc per r for a typical cross-sectional area of this value. So since the interaction is very slow, the density of detector particles will be very high. So in small amount of in small volume, they fill so much density, so much detector particles. And since we have cosmic rays, cosmic wave background, microwave background, all this, to avoid all this, the detector particles will be very deep inside the earth. So, and we have a formula for energy transfer, where small m is mass of dark matter particle, v is the velocity of dark matter particle, capital M is then mass of detector particle, and theta is the scattering angle. So in this, according to this formula, we want the more energy to be transferred. Only then we get the it will be confirmed that some particle has struck a detector particle. So if we apply, if we take maxima, we get capital M to be small m. That is, mass of the detector should be approximately equal to mass of the detector particle. So if we keep that constraint, and if theta is 0, that is, if it is a head-on collision, then we get the maximum energy transfer. So if any scientist is searching for WIMP particle whose mass is theorized to be 2 to 1000 GeV by c square, so the best detector is xenon, whose nuclei has mass of 123 GeV by c square. So this is the theory of energy transfer mechanism. So there are experiments like large underground xenon experiments, LUX experiments, which tries to detect WIMP particles. So they use 170 kilograms of liquid xenon, and it will be very cool and cryogenic, so that the speeds will be reduced, speed of the dark matter particle will be reduced, and there will be high chance of collision. So what happens is, when if any dark matter particle like WIMP collides with xenon, we get electroluminescence photon to be released. So we get some lights being flashed. So then it's confirmed that WIMP particle is existing. But after construction of that detector, even after 2 years, there was no positive results. So right now, what the scientists are doing is they're increasing the sensitivity by putting 350 kilograms of 3,500 kilograms of liquid xenon at very deep of depth of 1,400 meters. So this might be working in another 1 year. So other such labs are, as mentioned, Snow Lab, GSNL, all these labs are similar, which are trying to detect some other particles. And Xenon and Zeppelin are having similar mechanisms. Now coming to other technique, that is creating dark matter particle by mimicking the conditions of early universe. So hello, am I audible? Hello.
Yes,
Yes,
yes.
we can hear you.
So in this method, what we know is, so by Einstein's mass energy equivalence, we know that E is equals to mc square. So matter and energy are convertible. So if we provide enough energy in particle accelerators, there is production of new matter that could be done. So even scientists are trying to detect and create WIMP particle also. So now we know the mass of WIMP particle is around 100 GeV. So if that has to be created, then the proton-proton collision should be that is, the proton-proton collision should create an energy of 100 GeV. So even if WIMPs are produced, we can't see WIMPs because they are non-baryonic and they don't interact with EM waves. So what scientists do is they apply simple method of conservation of momentum and energy also. So in this image you can see, so if this is the proton collision, this center, after collision there will be scattering of newly created particles. So if WIMP particle is created, then we see some detectable particles to move in one direction, and in other direction there will be nothing to be detected by the detectors. So there is some imbalance which is seen by the detector but not happening. So then scientists easily infer that there has to be some particles which are not able to be detected to be created and scattered in opposite direction. So in such manner, scientists come to know that WIMP has been created and they'll detect in this manner. So this is some indirect method to detect and create WIMP particle. So this, what I've said, is the very basic and summary of what research papers I have learned, and this is large underground xenon detectors. So this will be the container of xenon detector, where it will be filled with liquid xenon. So if any dark matter particle is hit, we see electroluminescent photon to appear. So in this manner, we see that dark matter can be detected. And moreover, we know that universe is in ocean of dark matter. So in this picture, we can see that if the galaxy is so much, we see dark matter to be so much of size. So the galaxy itself is submerged in the ocean of dark matter. So in one small cross-sectional area, we should know that actually so many dark matter particles will be passing through that cross-sectional area. Even through us, dark matter will be passing. So that's what energy transfer mechanism tries to detect, and that's all. And indirect experiment, actually what to tell is, so WIMP particles is theorized to annihilate itself. That is, if WIMP will meet its anti-WIMP, so they'll annihilate to give energy. So that energy will be in gamma ray wavelength. So we have Fermi Gamma Ray Telescope, F-flat, and Fermi Gamma Ray Telescope. And even if WIMP gets to decay itself, the products of WIMP will be got by Fermi Large Angle Telescope. So this telescope can detect products of WIMP decay. So in this manner, we try to detect WIMP products. And even other detectors are ADMX, PVLAS, CERN, Axion Solar Telescope, which detects axions. So these are other indirect detection experiments. So that's all.
Thank you, Sagar. You did an amazing job. Yeah, that was very articulate, very nicely put. Do share your paper on the journal club. Does anyone want to, quickly ask him something or comment on that?
Sagar, it was very good. Just one query. The standard cosmological model, this lambda CDM, so they say it is all cold dark matter. So what is your opinion? The other types of dark matter are negligible or what? Because the standard model considers only cold dark matter.
Yeah, you can see that in classification of dark matter, cold dark matter moves at very slow speeds. Actually, cold dark matter is the most promising matter, because 90% of that cold dark matter is theorized to be present. That's because only cold dark matter can form lumps and hold galaxy together. In hot dark matter, particles move at very high speed, so they can't form lumps and they can't form such clusters. So that's why. Oh, sorry. Wait, I'll share the screen. Can you see the screen?
We can see the screen. We can see the screen.
So classification of dark matter here, cold dark matter. So actually 90% of dark matter is theorized to be cold, and WIMP is one of the candidate in cold dark matter. So actually cold dark matter only exists, and hot dark matter doesn't exist. Even if they exist, they doesn't contribute to galaxy clusters.
Thank you.
Any other doubt? Any other questions?
Hi, Sagar.
Yeah, bro.
Actually, I have a question. It's kind of vague question. I
No
don't
problem.
because I am completely new to this topic, dark matter, dark energy. Does this things exist, or all this whatever is going on is a kind of hypothesis? Like, yes, it is there, but we don't know.
Actually, no dark matter particle is still found out. So we can't say that exists or doesn't exist. But one promising thing is gravitational lensing, because this in some parts of galaxy, light is bending by itself. Then what is the reason for that? If dark matter is present, only then it can bend. So we can't neglect that also.
Yeah, even we don't have the proof that yeah dark matter is doing, right?
But dark matter is a matter, no. Actually, I've written how it is a matter. Can you see this?
Yeah, I can
And
see.
a main observation done by many scientists was that energy density of this missing thing was inversely proportional to cube of dimension factors. We know that matter has volume proportional to matter density. Matter density it is, sorry. Only matter density has volume proportional to cube root of length dimension. So when they compare the energy density of that missing thing, we get that dimension to be mass. So that's why it is called as matter, and it is supported by gravitational lensing also.
Okay, okay.
Yeah, can I come in, Sagar?
Actually, did I clear?
Sagar, can I add a
Yes, sir.
point? Can I add a point, Sagar?
Ask, sir.
Yeah, no, not
Yes,
ask.
yes,
I
sure.
just want to add what Vishwajit is asking. It is a subtle thing, a difference. What he's asking, does it exist? No, actually, there is no doubt that dark energy and dark matter exist. What is doubtful is the nature of it. So, absolutely, there is no chance that does not exist, because he has also shown the velocity of galaxies and how is the difference, and also we know the dark energy part. So the key problem is what it consumes. That is the doubtful. There is no doubt about its existence.
Okay, okay. Thank you so much.
So anybody else have any questions?
Sagar, like more than a question, I wanted to tell like nicely done.
Thank you, Vishesh.
Yes. So I think this is what the core of Journal Club is. So to be able to really just read one or two papers in a lot of depth, and then explain it in the best way possible. So yeah, good job. So I think we'll close here since it's getting slightly late. But I just want to make a couple of announcements. There are only 19 people online, but it's okay. So number one is, like I said, we're going to the last week. So first of all, there is going to be a survey form. So this is important because we also want to know what you guys want to do in the last week. So I mean, we had some things in mind, but we want to keep it really informal and flexible. We won't be inviting like big guest lecturers. We'll just try to give you as much technical training as possible. So fill in the survey, guys. It includes a little bit of feedback about equinox and nakshatra, but also it has a question about if you had to learn one technical skill, like some people discovered Jupyter notebooks for the first time, some of you learned LaTeX for the first time. So what would that be? So we know what to deliver after in the last week, but also after equinox, what we can give you guys in terms of help or support. So that is number one announcement. Another announcement is I'm going to be personally DMing a few of you for a small interview about your experience in Equinox, and also because I just personally have some questions and would like to get to know you guys a bit better. So if you get that personal message from me, you can just come on board on a Zoom call or whatever. But if you, on the other hand, you are interested to talk to us on the core group, or you would like to share your experiences and take initiative and share some feedback on a video, please DM me instead, right? So if I don't reach out to you, you can still reach out to me, and we'll schedule a Zoom session for just this and to discuss, what more needs to be done in this field. I want to know what you guys are facing, what troubles or problems you might be having in your college experience, what more is required in your academic training, and all of those things, basically so that we can make decisions from our point of view. So that is the next thing. Basically it's a video call where you have to just talk about your academic experience. And last but not the least, happy World Space Week. So tomorrow is October 4th, and every year from 4th to 10th of October, people celebrate World Space Week. So it's a very big thing. You guys can look it up. There is also worldspacweek.org that you can go to. So Nakshatra is collaborating with National Space Society, which is actually directly one of NASA's organizations. So we are going to bring you guys some nice events. It's obviously optional, but if you can we want to make it available to all Equinox participants. So there might be a couple of debates, space ethics, space policy, the big questions of what to use as a fuel for space travel, whether at all it is ethical to go and habitat, go and start a whole civilization on another habitable planet. So basically all these questions, so we're going to be tackling a week full of these big questions. There will also be some prizes for the winners and so on. So it's just a fun thing, but also filled with learning. And as you all know, tomorrow there is anyway a session about orbital mechanics and rockets. So please join that. So yeah, those are the three, I guess, announcement. World Space Week also has an essay writing contest and something called MaxQ, which I think some of you will find very interesting. So basically on spot, we will give you a topic related to technology or space, and you have to try talking about that in 3 minutes in the best way possible, right? So you guys, for example, today took maybe 15-20 minutes explaining a very complex topic, and you did a great job. But if you really had to condense that information, maybe 15 pages worth of knowledge, and if you have to condense it into 3 minutes, how well can you do? So it's called MaxQ. It was actually invented by Dr. Ravi, who is a NASA scientist we recently interviewed. So yeah, just join us, and it'll be fun. So finally, I just want to say all the best for your last week, and we're very much looking forward to what you guys do in your student seminars. It can be 40 to 50 minutes for your whole group if you want. So you can start giving us schedule, if you want it on 12th, 13th, tell us which date you want your cohort final seminar, and we can start putting the timetable together. Okay, any questions regarding any of those things?
Can you please one last time repeat the first announcement?
Yeah, first is just that I'll be sending a Google form. It's basically a survey. Basically, you should be, you'll be giving some feedback about Equinox and Nakshatra. But there is also an important question about what technical skills you want to acquire. And we are going to do our best to try and give you that support. For example, if there is a programming language or a simulation, I don't know what you want to do, right? So technically, what do you want to get better at? If you just name that, we will try to include it in the last week, basically. And if we can't include it in the last week, we will, create a course, create something else, some other way to support you guys. So yeah, please, it's mandatory. Please fill the survey. Yeah. Any other questions?
Yeah, during Dr. Ahmed's lecture,
Yes.
announced that there will be some forms and all indicating the future courses. Where is that actually?
Oh, yes. We will be bringing that to you soon. So there is basically a list of courses that we will be launching this year. So we will just share that with you guys. But like I said, the survey is very important because what we create depends on what all of you want. So if you have some feedback, that would be wonderful. So we can also start making courses or designing such programs, but in a better way. This is actually one of the first times we're doing it. Equinox is pretty new to us. Like, we've not done anything this intensive before. So we are still learning, and we would definitely like to bring better experiences to you guys. So yeah.
Sita, like I had a doubt. Like one of the team members asked this to me.
Okay.
During the final presentation that we'll have to give as a group, right, after the 4th week.
Mm-hmm.
So there, like, will each one of us have to give our own point of view, like what we've read, or as a group we can have like 2 or 3 people giving like introduction kind, like how you say the descriptive part, and later as like followed by those people will be like actually technical part. Like, should we divide the work among the group of explaining different parts?
Ideally divide the work amongst your group. So someone can do the intro, someone can do the first slide, someone can do the second slide. It can be like that, or you can take chunks of it and give it to a person. It totally depends on your group, but hopefully as many people as possible you try to involve. That's the goal. Just try to involve, because you have 40 minutes time now, so you can easily include at least 10 people to present, even if each person just speaks for 4 minutes. That's still 10 people. So yeah, please do that. Anybody else? Anything? Any other questions? Okay, so if nothing else, just keep in mind these three things, and we will see you in the next couple of days. Tomorrow there are two lectures. One starting at 6 o'clock by a research fellow from Ayuka again. She is going to be talking about gravitational wave detection. Kanchan Soni, and 8 p.m. is Karthik Tiwari. He's going to be talking about orbital mechanics. I know it's a little bit tight, guys. We are sorry, but Equinox is almost over, so please put up with it. It's, yeah.
One question. There was supposed to be a GR continuation sometime.
General relativity, is it? You want one?
No, there was some math thing which was left half, which wasn't touched actually. The presenter the other day wanted to do present it that
Correct.
day only, but
That
then
was Vikrant. Yes, that was Vikrant,
yeah,
who is not yet finished general relativity mathematics. So
yeah.
mostly we will do that this week because there's quite a lot of time. So I think Monday or Tuesday we can schedule his talk.
Okay, I just wanted to know when it would be.
Yeah.
Excuse me, Sitara. What about Sanskrit one?
Oh, okay. We will try to put that in the last weekend, guys. So next Saturday, Sunday, we have it completely free. So yeah, I think we will be able to do that. Science and
Okay.
Sanskrit. Yeah.
Okay. Yeah.
Yes. I remember. Anything else? That's it, right? Okay. So in that case, we'll wrap it up. I just wanted to also personally thank all of you for being so active. And when we first thought of the timetable, I don't know what I was thinking, but I thought it would be nice to have like a journal club, extra discussion sessions, trying to replicate as closely as possible a very physical conference or a physical summer school. So yeah, congratulations. I mean, at least 20, 30 of you have been extremely active. So we are very happy about that. So yeah, thank you. Okay, guys, good night. That's it from my side.
Good night.
Good night.
Good night. Bye.
Good night.
Thank you. Good night, all of you.
Good night, guys.